In this section, we will study the open-closed principle, attributed to Bertrand Meyer. This principle states that software entities such as classes, modules, functions, etc. should be open for extension but closed for modification. This may seem confusing. How can we extend a class without modifying its code? First, we analyze what it means for an entity to be open to being extended. It refers to the fact that new behavior should be able to be added to an entity in the future. Code that does not have this feature regularly has fixed behavior, which we must modify every time we need something new. On the other hand, code that is closed to modification allows us not to have to modify the source code to add new functionalities, and in fact, we should not modify the code unless it is to correct a bug. This is the only case in which it would be allowed to modify the code. You may wonder, why would you want this behavior in your projects? There are several benefits to using this principle. One of the main ones is that it will be less likely that we introduce new bugs into our system, precisely because we will not have to touch that code that was already tested before. Another benefit of this principle is that it will prevent us from having problems with systems that are already using the code base we want to modify, as we will avoid problems due to the use of incompatible APIs in their different versions. You will also see a significant change when working with conditions in your system, as this will be drastically reduced, as we will see in the practical example. There are some approaches that are usually followed to apply the open-closed principle. The first one is through the use of parameters. We see on screen an example in which we perform an operation of two numbers. As you can imagine, this is a very concrete implementation, as we could only obtain a single value as a result. By adding parameters to the method, we see that we can use these to return more than just one static value. With this simple change, we can already modify the behavior of the method without having to modify the source code. Another approach to the open-closed principle is to use virtual methods, which are part of C# syntax or are already predefined in languages like Java. In this example, we have a base class called demo, which defines behavior through the calculate method. We have added the virtual keyword so that we can override this method in case we need to. Next, we define a new class that inherits from the base class, and through the override keyword, we can modify the behavior of the base class to perform a completely different calculation than the base class does. This can be applied to any method we define and as many times as we need. It is worth noting that this approach is entirely based on inheritance, as it is the only way in which we can modify the methods of the base class. A very similar example is the use of an interface that defines abstractions in our system, and it is the implementing classes that define the behavior. Another approach is through dependency injection. In this approach, the class that will execute certain functionality is passed through the constructor and assigned to a private field that will allow us to maintain references when we need them. In this specific case, the class is responsible for executing a method called calculate, and it is not even necessary to create a new instance of the class, as the control of the lifecycle of the reference will be done from another place. Again, with this approach, it will not be necessary to modify the behavior of the demo class. The last approach we will see is extension methods, which allow us to add functionality to some type we need, as in the screen example in which, through the extension method called workCount, we use a new method for the string data type, allowing us to calculate the number of words in a text input. This without modifying the base string class. Now, it is also essential to talk about the considerations of this principle, since, when we are learning, we may think it's good to apply all the principles in all projects, even if they are straightforward applications. First, we must always try to maintain a balance between the abstractions of our system and their implementations, that is, the concrete classes. We must also remember that abstractions create complexity in systems. because we define the abstractions in such a way that they can be as flexible as we need them in our different cases. If we must take these considerations into account, how can we discover when to apply this principle and when not? How can we avoid falling into the temptation to want to apply this principle over and over again without really needing it? Because look, I suppose that in this figure displayed on the screen, the blue squares represent the abstractions in our system, while the yellow squares represent the implementations. Do you see anything strange in this design? The problem with this design is that it is what I warned you about earlier. This principle is being overused by wanting to make everything completely flexible. And in many cases, we may not even have more than one concrete class implementing the abstraction. How can we avoid this? The recommendation is to start by creating the concrete classes or the specific functionality needed. As the system is modeled or developed, you will discover that there is behavior that can be created in the form of abstraction, meaning it can be generalized to cover different cases. However, we must consider a rule, the so-called Rule of Three. And this rule says that a general-purpose solution or abstraction should not be created until at least 3 cases require this generalization. This is because with only 2 cases, we would not have enough information about what may vary when using the abstraction. That is, we could be creating a not-so-good abstraction. Let's get to know this principle in a practical way. Let's look at the open-closed principle in a practical way. For this demonstration, we will return to the project we saw in the previous section, this application that was responsible for calculating how much commission is due to a certain affiliate according to the sales made. On this occasion, let's suppose that the owner of the application or the person managing the application asks us to add a new type of affiliate. Remember that we currently have 3 levels of affiliates, the basic level, the silver level, and the gold level. He is asking us to add a new type of affiliate, obviously with its respective operations to calculate how much commission is due, and he is also indicating that later new levels could be added, such as the ruby level or other types of levels as part of the affiliates. Okay, let's improve our application so that it can accept this requirement from our client, and we will do this step by step so you can see how we develop it, at least in this project. What we're going to do first is create a base class, which will be the class responsible for defining what the common features will be for all affiliates, or so that we can perform the calculations for our affiliates. For this, we will create a new class as part of our project. Let's call this class, for example, Calculator, and let's make the class public. We need to see what things we need as part of our class that we have created called Calculator. First, let's add the keyword abstract to indicate that we have to use this class only through inheritance. That is, we will not be able to create new instances of this class called Calculator, but it will be only our template for the classes that inherit from it. Secondly, let's quickly review Report Engine. And let's see that the definition or that each of the cases we are using here always uses a logger. Therefore, we need an instance of this logger to work or to print, in this case, through the log method, each of the messages we need. As part of our abstract class, let's create a constructor called Calculator, and let's indicate that we want to pass an instance of the logger type as part of the constructor. Let's also create a field, protected read-only, called logger, and called _logger, or of the logger type. Once we have done this, we simply assign _logger equal to logger through the constructor. Let's continue reviewing Report Engine, and we see that as part of each of the cases we have here, we are also using a property, Total Commission, which is part of this same class called Report Engine. Therefore, we also need an instance of Report Engine to carry out these assignments we have here if we want to maintain this same logic. Returning to our new class, let's add a new parameter. I will place it before the logger parameter. Let's indicate that we need an instance of Report Engine as part of the constructor. We place it here, and we will create again as protected read only the data type report engine called _engine. It can be engine or it can be report engine as well if you prefer to make it more descriptive. And finally we will indicate that _report engine will be equal to engine. In this way, we already have our base class where we define our constructor and its different fields that we will use throughout the classes that inherit from this class. Finally, we're going to define a method that carries out the processing of each of the calculations we see here. We will indicate that we want an abstract method to override it later, of void type, called calculate. As part of our method, we will need an affiliate data type, and we will call the parameter affiliate. This is so that this method receives an affiliate and performs each of the calculations that are part of these different cases. Since the method is defined as abstract, we ensure that it will be implemented differently in each of the implementations that inherit from this class called calculator. The next step is to extract this logic that we have here, because currently this switch performs each of the calculations. In our current problem, we are asked to add more affiliate cases or different affiliate levels. If we wanted to make one of these changes, we would have to come here, copy this case and add different cases to this switch. This method becomes more complex and gains more complexity because we are adding many cases. This is not very good because we would also be modifying our reporting engine. In one of those cases, we could modify the name of a property or a case that is not the one we are looking to modify. This could result in incorrect calculations that do not correspond to what the client wants. We have to extract each of the cases into a class for each of them. To achieve this goal, we are going to first add a class called Basic Affiliate Calculus, or the calculation for basic level affiliates. We turn this class into a public class and indicate that we want to inherit from calculator, which is the class we implemented earlier. We implement the abstract class. We also have to implement the constructor so that we do not have any type of error. Once we have our constructor, we also have this method that we indicated had to be abstract. We are already overriding it through override to carry out a concrete implementation. In the case of this specific calculate method, we will return to report engine. We see that what we are doing here was carrying out a log and then the commission calculation. We cut these two lines from the basic level and paste them as part of this method called calculate. Obviously, here we have some problems because we do not have a reference to a property called logger. We have to use the reference that we do have, which is _logger. Remember that this is established in calculator. Here we have our reference, which is this field called _logger. Once we have done this, we also have here a field called total commission that is not part of this specific class. What we have to do is access directly to report engine, which is the reference that contains the total commission property. In the same way, we no longer have an affiliate info, but we will work directly with the reference we pass as part of this parameter, which is equal to affiliate. Thus, we will carry out the logging part and the calculation of the total commission. We must repeat this same step for each of the cases. I'm not going to write everything, I'll just copy and paste what we need. Let's create our new instance with our new class called Silver Affiliate Calculus. I will copy here the piece of implementation code, but we already saw how the correct implementation of each of these classes is carried out. In this case, I already carry out the part of the operations for a silver level. I go back to report engine and I'm going to remove these lines that no longer make sense to have here. Finally, I will add my class. This class will be called Gold Affiliate Calculus. I will also copy and paste a piece of code. I have here my new class called Gold Affiliate Calculus, which inherits from calculator and implements the corresponding operations. Once we have done this, I quickly return to Report Engine. I'm going to remove this implementation that I had in my case. Look how our section of this switch is getting shorter. Next, the next step is to implement or modify this switch, since we also need to create a direct reference to each of these classes. In the case, for example, of the basic level, we will indicate that we will need a reference called basic calculator, which is equal to a new instance of basic affiliate calculus. We have to pass, first of all, report engine, which is in itself the reference from which we are calling our calculator. Subsequently, we already had an instance of logger created. Remember that it is in the format of a property. Here we have it, so we can pass the name, which is logger. We pass this reference, and with this we are creating the new instance. Finally, we will indicate that we want basic calculator to call the method called calculate, and we will pass the affiliate information so that this calculation can be carried out. We already have this part ready. Look how the code has been reduced to just a couple of lines. We will do the same with each of the affiliation levels. I will copy the code that I already have prepared previously, so I remove this section. Look how the code is quite similar. An instance of each of the calculation engines is created, and then execution of the method called calculate is carried out. The same goes for gold level affiliates. Let's check that everything continues to work correctly. We start the application. Here we have the application running, and we see that we have a satisfactory calculation. So it means that the application is working correctly with these changes we have implemented. We have already taken a big step in improving the application. However, we still have the problem that if we wanted to add more affiliation levels to our report engine class, we would have to continue modifying this switch that we have here. So, why not take into account the single responsibility principle and let someone else take care of creating each of these types of affiliates? We're going to use something called a design pattern, which is one of the simplest. In another section, we will examine design patterns, but let's have a general overview of this pattern, which is quite simple for accomplish this task. Essentially, this design pattern will be in charge of creating each of the corresponding instances as we need them. To achieve this objective, we will create a new class called Calculator Factory. This is a naming convention often used when applying this design pattern. We will make this class public and create a method that returns a calculator data type. Keep in mind that the calculator is the base class for the classes we created earlier, as they are implementing these concrete classes. This is an implementation of the base class, so we can return a calculator data type, and this data type can be any of the concrete classes. We will then specify that this method will be called create, because with this method we want to create each of the instances we need. Once we have created our method called create, we return to the report engine class and cut the previously defined switch. We paste it directly into our method called create, and we start to see some errors. The first error is that we are missing information about our affiliate to know what level the affiliate belongs to. So we have to pass the affiliate data type as a reference to this method and a parameter called, for example, affiliate. And also, as part of our implementation, we see that we need a reference to the logger. So we will pass a report engine instance as the second parameter, since report engine has a property of the logger type. Now we can use this logger as part of our factory. Once we have done this, we change the references. Instead of affiliate info, we paste the name affiliate. We could have kept the same name, but here we decided to change the name. And finally, to use our logger, we have to access through engine.logger. Let's do this with each of the references. So engine.logger and finally engine.logger. And also, as the first parameter, remember that each of these methods expects a report engine instance. So we could directly send this reference that we are passing as part of the parameters instead of this, which refers to the same instance in which we were. And this problem is solved. We still have an issue with the create method because it indicates that not all code sections are returning a specific value. And that's because we are missing adding a default case as the last case. What do we have to send as a default case? Well, we can create a new instance, an unknown type of instance. Let's quickly add a class and call it unknown affiliate calculus to indicate that we don't know how to perform a calculation of that type of affiliate. As part of this class, we will make it public and inherit from calculator again, implementing its different members. In reality, we are only interested in this calculate method, and here we will simply use the logger to send a message or to log a message that says unknown affiliate type. That's the only thing we're going to do as part of this special case. We return to our factory, and as part of our default case, we're going to indicate that we want to return a new instance of unknown affiliate calculus, passing engine and passing engine.logger, so that we don't have any issues. Once we have resolved this case that we see here, I ask you, do you think this class is ready to create different instances of affiliates or affiliate calculators? The truth or the answer is no. Look what's happening right now. In each of the cases we create a new instance of each of the calculators and we're executing a method called calculate. But in this case, our factory should only be responsible for creating instances, not for performing different calculations to see how much commission an affiliate gets. The first step we have to do is to remove the invocation of each of the methods that carry out the commission calculation. Subsequently, what we have to do is make sure that each case returns a new instance of the different calculations for each of the affiliates. Instead of creating a new variable for each of the instances, we can simply do a return to return a new instance of the corresponding type. Here, I'm missing an n. And we can apply the same thing for each of the cases we have here. So let's do it. With this, we are indeed returning each of the corresponding instances. We can also remove this break, as we won't reach it because we are returning the corresponding instance, and we already have a class that looks pretty good, that looks pretty clean, and that will only take care of one task, creating different instances according to the affiliate's level. Now that we have this solved or that we have this class ready, let's quickly return to report engine to complete our method called evaluate affiliate, since we removed the part of creating each of the instances from here. What we're going to do instead of what we had before is to create a new instance of our factory, which is called calculator factory. Once we have created the instance of our factory, we're going to create an instance called calculator, which equals factory.create, passing the affiliate information and passing the reference to this same report engine. This is because remember that in the affiliate info we already have all the affiliate information, including what level this affiliate is. We also need a reference to this as part of this method called create, since we are requesting it as part of our factory to carry out the initialization through the parameter. Now that we have this ready, we simply indicate that we want to execute the method called calculate, passing again the affiliate information, and with this, the operation of calculating each of the affiliates would be executed according to the affiliate's information. Finally, we could, for example, indicate that we would like to carry out the invocation of the log method and write something like, for example, complete. Once we have this ready, let's test our method to see or to make sure it continues to work correctly. Here we have the execution, and see that everything works just as it was working before, which means that everything is running correctly. With those changes we have made, we can now create our new type of calculation for the new type of affiliate. How can we do this? Well, I want you to pay attention to what we're going to do, especially in this class called Report Engine. We're going to create a new class as part of the project according to the client's request, which is to create a new type of affiliate, Diamond. We're going to indicate that we want to create a class called Diamond Affiliate Calculus, and what we're going to do is turn this class into a public class. We will inherit from calculator, just as we did before. Let's implement both the constructor and the calculate method. What we're going to do as part of this method called calculate is a series of operations. I won't write them from scratch, since I have previously coded the calculations so as not to have to write all of these. This type of affiliate has a set of additions that are quite good, such as if in a month, for example, we have a promotion of electronic items sales, and the products that the affiliate sold the most were precisely from this category, then we will give an extra percentage or a fixed extra amount. In this case, we are indicating that if the best-selling category is equal to electronics, this extra variable will be equal to an additional $50 for the affiliate's back. Here, we have already carried out the comparison that if the items sold were more than 30, then we assign a certain percentage plus an extra, and so for each of the cases. We see that it continues with the same line that we had before of calculating different commissions for the different levels of affiliation. And also, what we have to do as part of our project is to have a correct conversion. We have to add the new type to our enumeration called affiliate level. We will call it diamond equal to 3, which is the new value that would correspond to this value in the enumeration. Finally, as part of our class that is dedicated to creating the different instances of our affiliate calculations, that is calculator factory, we have to add this new case. We will indicate case affiliate level.diamond, and in this case, we have to create a new instance of Diamond Affiliate Calculus, passing again engine and engine.logger. In the report engine class, we're not going to do anything at all. With the great engine that we have created with these different classes that we have created, the truth is that this is the class that will not need to be modified anymore, because we are delegating different tasks to the subclasses. We are delegating the power to create instances to our factory, our new factory type class. We are delegating the calculation to each of the concrete classes, and with this, we already have a new level or affiliate added as part of our different available options. So, to test this new mechanic, let's change the level in report.json to diamond. And now that we have this ready, let's test the application. Look at how the amount given to the affiliate is already a higher amount than we had before. It is now equal to 450, which means that our application is working satisfactorily. Lastly, there are even more extreme ways to reduce the code we have as part of the project, specifically talking about our code in our factory that is responsible for carrying out the creation of instances. Notice that we currently have a switch here that performs validation through each of the levels to determine which case or what is the new instance that needs to be created. What we could do instead of this switch that we have here, I'm going to comment it out and paste a new code that I have previously created. What we can do is use reflection to carry out the creation of the different instances. Here, what we are actually doing is evaluating the affiliate level. We are using the full name of the class or the type as such, specifically, and we carry out the creation of an instance of the calculator type, passing the corresponding parameters. It's a slightly more complicated code, but it allows us to have an even more simplified part of the code. The only problem with this approach is that we must be very precise in terms of naming each of the classes, since if for some reason we change this nomenclature in which we first define the affiliate level followed by the word or words affiliate calculus, this section would no longer work as we are relying heavily on the specific name of the classes. We are thinking that all classes will have this type of name. First, the namespace name. Secondly, the precise affiliate level followed by the pair of words affiliate calculus. This is what makes our code work satisfactorily. It uses reflection to carry out the creation of the different instances, and if we test this application, we see that the application continues to work correctly. Basically, this is the open-closed principle. We have already seen it with theory and with a practical example. Let's move on to the next principle.